Okay, thank you for the introduction. I'm gonna talk about joint work with Sam Edwards and Hyo. It's a result on local mixing, counting, and equidistribution for homogeneous space of infinite covolume in higher rank space. I will explain what I mean by this. So the setup is that my G is going to be, say, connected simple. Okay, I'm supposed to
bigger. You can take your mouse book with you.
Is okay?
Yeah. The rules allow you. We're far away from you.
Like this simple linear group. And gamma is going to be Zariski dense. Discrete subgroup.
Can you guys see it?
Sorry?
I'm just checking that they can read.
And A is going to be maximal.
Mu is over Q or over R or over C or over QP or something?
Is all over real.
Okay, yeah.
A will be a maximal abelian subgroup that is diagonalizable over real. For example, G example, I mainly focus on the case R. And although this is not simple, but allow me this that R times space R will also my example later. So then A is going to be this angular subgroup. I can choose this one. And for this one, I can choose the product of this diagonal. And then dimension of A is called rank of G. So this is real rank 1 case, and then this is real rank 2. Then I'm going to use a notation A sub T. T is a parameter in R to denote one parameter subgroup. Of A. Okay, and now I looked at the quotient space, the quotient space G mod gamma, and this carries a unique G invariant measure up to proportionality. Up to proportionality, which where I will write MR, I measure. Then you get a unitary representation L2 G mod gamma with respect to the R measure. This is a unitary representation. G. And depending on whether this R measure has finite mass or infinite mass. So there are two cases. Whether this is finite or infinite. And in the former case, the only G invariant vector is a constant vector, and then this doesn't lie in the space in the latter case, and it belongs to the space in the former case. And we have the decay of matrix coefficient due to Harmon.
By the way, what do you assume about gamma? It's finitely generated or nothing? Finite in geometrically finite in some situations? Nothing.
So
at this point, nothing.
At this point, yeah. So for lattice case, you get this.
Yeah.
The latter case.
Yeah. So in infinite volume, this is a very subtle thing. You'll discuss it.
Right. So in the end, I'm going to focus on the finitely generated one, but I guess at this point here, I don't think I need it. Decay of matrix coefficient. This is due to more.
Your writing is shrinking. Keep it big.
Okay. I guess it's okay for people, but
yeah, my eyesight is very bad. You keep it big for me. Yeah.
Okay. Yeah. So you look at the matrix coefficient in L2 space, AT, F1, F2, where F1, F2 is for every F1, F2 in L2 in gamma. You look at the matrix coefficient, AT, F1, F2, and what this means is the integral of the following expression, which is a correlation function when xat times x, and I integrate with respect to Hart measure. Okay, let me write this way: en Hart x. In the first case, this converges to the Hart measure of F1 times Hart measure of F2 equals to infinity. And if this is finite, but on the other hand, if infinite volume, and the same theorem tells you that ETF1 F2 will go to 0 as e goes to infinity. Okay, so the motivation is, and you can ask what is the rate for this decay of matrix coefficient. So can you find a normalizing function so that if I multiply the normalizing function here, it converges to some positive finite constant? So let me make it more precise here. So thus there exists a normalizing function psi, let me call P. So psi is discrete one, a normalizing function psi from R to R. And secondly, locally finite measure, for a measure, it could be infinite, but could be assigning finite number to a complex set for locally finite for a measure. Say M1, M2, such that the following holds. If I multiply psi t, the matrix coefficient in this converges to the measure of M1 of F1, M2 of F2, or all F1, F2, which is a support function in homogeneous space. And the question is whether I can find this function psi and Fourier measure set this whole.
Psi doesn't depend on F1, F2 as well.
Psi doesn't depend on F1 and F2.
Why do you restrict to compactly supported now?
So you can ask the same thing. Like if you could just so your question is why not L1, L2, and then that's like plausible setup, but turns out that this is the correct setup because in the end you will get a statement for this one, F1, F2 in compactly supported. And on the right hand side, if you put like L1, L2 here, then it is possible you can find an example where this is infinity. So this seems to be a more reasonable setup.
Sorry, stupid question. What is the measure of F1? Is that just the integral of F1?
Yeah, right. So this is integral with respect to measure.
You want to both exist.
Huh? Sorry?
So you want one to both exist. So item 1, item 2.
Yeah. Okay, and then let me give you a known result. So known for the following cases when so gamma is a subgroup of ESL to R. It's not in a full generality, but say this is convex or compact. I will explain this shortly. And in this case, we have psi t. It's going to be e to the 1 minus delta t, where delta depends only on gamma. Delta depends on gamma, and so it's a measure M1, M2, which is called a Burger-Roblin measure. Whose higher rank generalization will be introduced later in my talk. So there was a Burger-Roblin measure in the rank 1 case, and this is due to OSHA. Okay, so what is this convex co-compact? So this means that gamma is now subgroup of PSL to R, and the associated symmetric space is hyperbolic space. So there exists, let me write it, gamma preserves. Maybe I should write it here. Gamma preserves non-empty convex subset of H2, and gamma will act co-compactly on this non-empty subset. So on which gamma acts co-compactly. This is the reason for this definition for convex co-compact. And from this, it follows there is a lemma in geometry group theory called Milner-Spark. It follows that gamma should be word hyperbolic in the sense of Gromov. And then there exists gamma equivariant embedding zeta going from the boundary of the Gromov hyperbolic group to the visual boundary of H. This is gamma equivariant.
If delta is bigger than a half, less than a half, delta bigger than a half. Then there's the Patterson-Sullivan measure.
Yes.
That's essentially this measure.
You mean this one? Yeah, this will appear as a component of this Burger-Roblin measure. Okay, and then we will probably get to this.
I guess there's always a Patterson-Sullivan measure. I apologize. But if delta is less than a half, then bigger than a half, then there's a square integrable eigenfunction. It's kind of useful. But otherwise, it's not there. Right, you'll explain the relation.
Okay. Oh, I forgot to mention one thing. So this property 1 and 2. This property 1 and 2 is called such property is called decomposition property. Which is given by, its name is given by O and Pan. The local comes from the fact that we're looking at the local functions we supported. Okay, so this delta is called a critical exponent. And then, so if you look at the discrete subgroup in PSA to R, you can divide this into 2 categories. The first one is called geometrically finite, and the second one is geometrically infinite. And the convex co-compactness falls into the first category, which is geometrically finite. And there are also known cases for the geometrically infinite.
To construct explicit examples of convex co-compact subgroup.
You mean here? Yeah. So
some example.
So example is you can take the what's called a quasi function, which is you embed gamma into get a PSA to right here. The PSA to R, like PSA to C. Then in terms of this, you have, say this is boundary of H3, and you can think of this circle, which is invariant under PSA to R. Think of like boundary of H2. Then if you put gamma here, and then you can make an inclusion for PSA to C. And then if you deform this, then previously, say this is a co-compact lattice, then the limit is something like this. But if you take if you deform it like PSA to C, then you get this kind of example. And in this,
you can also make Schottky groups. You just glue 2 circles as long as you don't have them tangent. Then it'll be finitely many circles. Schottky. The ping pong that Tits plays that'll give you these. You take 2 transformations which are far apart. The way you play ping pong, in this case, those are geometrically finite in the plane. It's a Schottky, it's a construction of Schottky. Very simple. That's much more complicated. More interesting.
I might mention in Schottky in the higher ranks, but I can explain more later. Okay, so what's the example for geometrically infinite case? Then let's say you have gamma 0, which is a fundamental group of a closed surface of genus G. You draw a picture later. And then say gamma is you take gamma a normal subgroup, and say this has which has infinite index, and this is the quotient is ZD. The picture you have here is, say, you have a GS2 surface, and then you take a cover, which in this picture that I'm drawing has a Z cover. So this is this covering is has a quotient Z, and then this gamma is going to be the fundamental group of this one, and gamma 0. It corresponds to this one, and then this is a result due to one time. In this case, you have So t is e to the d over 2 times, in this, okay, you can take more general surface, which is not closed surface, but I think in this case it's t to the d over 2. And then M1, M2 is a Burger-Roblin measure.
In this case, it's just one measure. Yeah.
All right. Yeah. Thank you. Thank you. Yeah. Yeah. So, yeah. In this case, it's our measure to coincide. Okay. Let me. All right. So now you can see that. Although I did not write it here, in both cases, you can take a more general setup, and then you can also see a critical exponent delta appearing in the asymptotic formula. And in the higher rank setup, what's going to play the role of this asymptotic formula is called a growth indicator function. So we give answer. So the asymptotic formula is given, will be given in terms of growth indicator function. Psi gamma, and then I have to spend some time explaining what this growth indicator function is. So let me give a brief recap of dynamics on first order boundary in high rank setup. Okay, so dynamics first order boundary. Which is G mod P, where P is a minimal parabolic subgroup. Okay, so let me start with the case when G is PSM to power. And A is case. And P will be the minimal parabolic subgroup, which I chose to be this upper triangle matrix. And now you have an associated symmetric space, which is H2. And here you have a boundary H2. And suppose you now you're given G. And assume that this is a loxodromic element, and then you look at the iterated action, Gn, Z action, and then you will see these 2 points, which is attracting fixed point and repelling fixed point. And then as I iterate this Gn, I take any point here, and then as I iterate G to the n, it will converge to these 2 points, which is called attracting fixed point, repelling fixed point. And then there is an axis which is preserved by this element G. And this is called the translation axis. And along this axis, the orbit moves by by a constant, and then this length is called translation length, which I'm going to call T1.
Bigger.
Okay. Yeah, so you have translation axis, and here you have 2 fixed points, and then the amount you translate is given by, say, length T1. So you get this 2 and translation length. And then conversely, if you have these two information, attracting fixed point and repelling fixed point and translation length, you can recover your element. So you can think of this as like where this encodes where things happen. And the translation length encodes how things happen. And now let's look at the case where you have another product, another vector, which is pxl to r. And the A is going to be the product of these two diagonal. Okay, P is also a product of this. And I'm going to call A plus the right chamber to write e to the t1, e to the minus t1, comma, e to the t2, e to the minus t2, where t1 and t2 are both positive. Okay, so that's positive right chamber. And then now you have, the associated symmetric space is a product of H2 and H2. And now you have a pair of element, and you will get a fixed point here and over here, and then you will also see a corresponding translation length T2. So now what encodes, what corresponds to the previous one becomes a pair of translation length, which is a vector, and we're going to call this Jordan projection. So in this case, you get a Jordan projection. Which is, in our case, is a pair of translation lengths. And then I'm going to call the attracting fixed point G, the YG plus. This is just the notation. Y is a twice. Okay, so YG plus is a notation. So algebraically, if G is conjugate to some element A, which is inside the right chamber, then the Jordan projection just corresponds to the log of A. And similarly, this is called the Jordan projection. Okay, so this is called this is a definition of Jordan projection. Okay, so not every element can be written like this, but in that case, you just look at the Jordan decomposition and look at the semi-simple part and then write it like this. And then you have a corresponding Cartan decomposition. So it can write KAL, where you use the decomposition G equals KA plus K. Then A is an A plus. Then you write mu of G of A, and this is called the Cartan decomposition. Sorry, Cartan projection. All right, and in our case, A plus is just a product of two reals. So I can write like this. This is a T1 coordinate and T2 coordinate. And the law introduces two following concepts. The first one is called limit cone. What is a limit cone? This is right S of gamma. This is a cone contained in the positive right chamber. This is a log of A plus in the Lie algebra, and then this is the smallest closed cone. Containing all the Jordan projection of gamma. You can write gamma. Okay, so you have A plus, and then if you look at every element of gamma and then plot the Jordan projection, and a smallest closed cone containing those Jordan projection is called the limit cone of gamma. This is by Benoit, and there is something called okay. So what's the example? Okay, maybe let me not write example remark. What is the limit cone if gamma is a lattice? If gamma is a lattice, meaning that the Hahn measure is finite, then E cross is just gamma is the whole right chamber. So when you study that, it's not a very interesting notion. And there's also something called limit set. Maybe. Okay, so limit set. This is also due to Benoit. You write lambda sub gamma. This is a subset of the first number boundary. This is the smallest set, closed set, containing all the attracting fixed points of loxodromic elements of gamma. And this is again, if gamma is a lattice, the limit set is the whole first number boundary. And finally, the growth indicator.
If I just take the action of gamma on G mod P,
yes,
and take the closure of a point, I mean, can I just make a much more crude definition of a limit set, like you do in
so you can, yeah, you can do that. So you can take the accumulation points of gamma, but it's, so this is a unique gamma minimum set. So
that's a part of it.
Yeah, so yeah, if you take the closure of gamma orbit, then you will see a limit set inside, but it can be like
small.
Yeah.
That's right, I don't know. So for this limit set, so is it possible to describe this by using flags?
This limit set?
Yeah, using flags.
Sorry, I think I didn't understand what
Q over P is a flag, right? So if you use language of flags, is it easy to describe this set?
I think in some cases you can, but I'm not sure if I'm thinking of the same concept. So, okay, maybe I'll get to the example, and then.
The complicated set. This is kind of, even in rank 1, it's a fractal set.
Yeah, but yeah, I'll get to an example. For example, I don't know if I will get to this, but. Okay, so for at least Anosov subgroup, which I did not define, you have like embedding of, this is homeomorphic to the boundary of gamma, and then okay, so for gamma, if gamma is Anosov, then you have some homeomorphism of this in the limit set. So it has.
You're going to define Anosov first. It's kind of important.
You mean now?
No. Maybe when you define it, then give us this example.
Oh, okay. Yeah. Maybe I come to this like in the example. Okay, so the growth indicator is due to count. So growth indicator is the following function. It's defined in the following two steps. So first you take any cone, for any cone, say C. C is an open cone inside A plus. You take cone C and then you look at the Cartan projections mu gamma and then look at the exponential growth rate. So, okay, so what is HC? HC is the exponential growth rate. You look at the number of element gamma in gamma such that Cartan projection takes a size less than t. To get, take a logarithm and divide by t and it continues as t goes to infinity, and you define as h sub c. So this is the exponential growth rate of this number of mu gamma, and you truncate up to t, and then second, if we take a point u inside A plus, how do you define the growth indicator? If it is a unit vector,
mu gamma has to be inside the C. You forgot to write, yeah.
Yeah, thank you. Mu gamma is contained in the cone. Okay, so this now if u is a unit vector, you take infimum of this HC, where C is an open cone containing u, and if u is not a unit vector, you multiply by the norm of u to make it a homogeneous function.
That's just localizing in a direction.
Yes. So yeah, it is if you have a direction u, then you look at like a small cone containing u, and then some analog of critical exponent. Okay, so now I can describe the answer for 1.
I guess this C gamma of u can depend on u. That's it.
Psi gamma.
Does it vary nicely with u?
Yeah. It depends on u, and yeah.
Continuous.
It's continuous, yes.
Okay.
So if gamma was a lattice and C was the whole positive Biot chamber, you would be counting loxodromic elements whose translation length is less than or equal to t?
Yes.
Okay.
Yes. And then I forgot to write if gamma is the lattice, then this growth indicator is actually a linear function, which is written as 2 rho. This is convention of writing sum of positive roots. Rho is the half sum of positive roots. Okay, now I can give an answer for.
Just to, since Francisco asked this, he would always, if you're counting just the lengths, you would divide by conjugation. So you take conjugacy classes. That you're not doing. You're counting elements.
So are you asking whether I'm counting the conjugates? Getting conjugates?
You're counting different conjugates as different.
Right. I'm counting a conjugate element as a distinct element.
Yeah. Okay.
But also psi gamma is continuous only in the interior of the limit cone. I mean, you probably should mention that it is minus infinity outside of the limit cone, but also continuity holds only inside the interior of the limit cone. So the behavior along the boundary of the limit cone is more mysterious.
Okay.
And as a function of u in the interior, it's continuous, absolutely continuous with respect to some measure.
It's like upper semi-continuous. I think whether it was upper or lower. Anyway, but this implies this implies a continuity in the interior of the limit cone, but the boundary is not known. Okay, so that now I can give an answer for if is Anosov, which I did not define yet, then the answer for 1 is given by the following. So psi of t is going to be t to the r minus 1 over 2, where r is the rank of G, and then it's going to be e to the 2 rho minus psi gamma of tu, where my one parameter subgroup AT is written as x of tu for u inside the interior of limit cone, and u is a unit vector. Okay, so this gives the first asymptotic. Okay, now I go to introduce Harrison-Sullivan measure in the higher rank setup. But for the clarity, I'm going to write something technical, but whenever I write...
When are you going to define Anosov?
Oh, Anosov. Or maybe I just do it now. I just postponed it because a lot of techniques we use doesn't restrict to Anosov group, but Zariski dense. Right. Yeah, but yeah, I know.
All right.
Probably you should just define it. I mean, like you keep using the words Anosov and not defining it, right? Just define.
Okay, so definition we say gamma is Anosov. So Zariski dense is subgroup is Anosov. If there exists a continuous gamma equivariant map zeta. Okay, so first, if it is word parabolic, and there exists limit map, which is gamma equivariant, and going from the boundary, remote boundary of gamma to black manifold first number boundary, such that there's some transversality condition that if you have two distinct element x and y are two distinct element in the remote boundary, then the image of the limit map should be transversed if they meet in a torus or they are in a unique open G orbit. Okay, so it's a unique open G orbit. This right down. So this belongs to the unique open G orbit inside the product of.
This is a condition which is trying to compare the word metric to the geometry.
This, yeah, there is.
No, the Gromov boundary would be the boundary relative to the word metric, I assume.
Yes.
So if I take you out of this world for a second, suppose I was in a variable negative curvature manifold, variable,
yes.
Then the boundaries, these boundaries are very different constructed. I mean, there's this Margulis measure which tries to fix up the fact that various measures on the boundary are different. So here, we're not in variable curvature, but we're in higher rank. I'm just trying to get an intuition what this is. Is this your definition?
No. Okay, so there are equivalent definitions, but I'm taking the most convenient one for mine. So you can, there is an equivalent definition which is, let me just write it. So if you have a root, let's say like pi is the root system, a positive root, then for every.
Yeah, I mean, computing the, if it's a free group, I sort of know what the Gromov boundary is. If it's is this something I can check? If you're given gamma, can we actually check that it's an Anosov?
Using this one?
Well, maybe the equivalent will give me an easier definition.
Yeah. You can check this. I mean, yeah, you can. Yeah. So maybe I just give a definition. I mean, example. You can check.
Okay.
Okay. So
I think we should spend some time on this because this is an important notion in theory, I believe.
Okay.
I mean, if I understand what you're doing, is in rank 1. If you're in hyperbolic space, you have geometrically finite, you have geometrically infinite is a bit problematic, but maybe you can do something. Now you're going to a higher rank where we don't have the notion of the convex geometry fails miserably. Yet you're still trying to talk about this counting and the boundary. And it seems that what you're saying is you'll succeed if it's an Anosov.
Oh, yes.
So we need to know what an Anosov is.
Okay,
I mean,
so
but you should also mention, I mean, so this is Anosov with respect to P, and then maybe give an example for SL2 times PSL2R times PSL2R, because in that case, we have a complete classification. And then this definition is due to, Laborie and then Kishar-Winhard. That should be mentioned, I think.
All right. So we outsiders, or at least I'm an outsider. I'm trying to understand in higher rank. This is a theory, just for my view of this, is people have tried to generalize a theory of geometrically finite convex co-compact to higher rank.
Yes.
It's been very difficult, and this is part of that industry. And
yes.
So one of the things that comes out is that if you're Zariski dense, we like these groups that are subgroups of an arithmetic group that are Zariski dense. They come up naturally in all sort of context. But usually we can't tell, even in the rank 1 case, if I say, is the group geometrically finite? No clue. So the question here is, if we're in higher rank, you've got a substitute or a sufficient condition to actually execute a lot of the theory, which is quite striking. Then I hear the word Anosov all the time, and we need to understand what it is. Right. So give us give us this equivalence and then some examples. Yeah.
Okay, so the equivalent definition is okay. So here I'm taking minimal parabolic subgroup. So minimal parabolic subgroup corresponds to like the whole simple root. So I'm going to write this is a part of the simple root. Then for every root I take, and if I look at the projection, sorry, not the projection, but look at the Cartan projection, which is an element of A, was a vector, and then evaluate it with alpha. Then this direction is trivial, so this is going to be less than C times the word metric. Yeah, and then you want that this is less than C inverse gamma plus minus C.
So this is some quasi-isometry condition.
Yeah. And then you can, this is one of the equivalent definition provided by, I think this was first introduced by Laborie, where he studies a Hitchin component, and then further generalized to the word hyperbolic group to by Kishar and Winhard.
Okay, so this requires that the word metric and your cone and your Jordan be quasi-isometric in some.
Yeah.
Okay, and when, so give us, okay, so that's equivalent.
That's equivalent.
That's easier for us to understand, I think.
Yeah.
Can I ask, so the limit map, you say it has some transversality property.
Mm-hmm.
I suppose it has to have some continuity property, but is there something, transversality is the only thing that you care about, or is there
this is
a relation between like taking powers in if you take powers of an element in the group gamma?
Yeah, so this is, okay, first, this is continuous. And then I think this should be continuous. And then in general, you have to impose this condition that you mentioned, like you have you have like a hyperbolic group, and then you have first of all boundary, and then there is this gamma itself carries like dynamics in its Cayley graph, like attracting point, fixed point, and then this should carry to the image, and then they call this like, dynamics preserving. But if you assume the Zariski dense condition, then this is the only condition that we need. Okay.
Okay, now an example.
Okay, example.
You've got till 12:15.
Yeah, I thought I would finish. I thought I would finish earlier.
Now there's a learning seminar. We want to learn what Anosov is. Then we'll understand your theorem better.
Okay. So example, probably the maybe first group that you're mentioning.
Maybe do the PSL2R times PSL2R example. I think that's more interesting.
Yeah, I'll do it, but I didn't intend.
You do what you want to do.
So I didn't.
Okay.
So just to clarify, I didn't intend to do examples, but okay, let me do Schottky and picturing.
Yeah, interesting.
Then thirdly, what he mentioned, I think I was trying to only do this one, but I have to improvise this. So Schottky group. Okay.
And just to be clear that this kind of quasi-isometry feature in the lattice case, if there's cusps, there's always a problem. But if there's no cusps, then you have this feature. So you're kind of in infinite volume and looking for this feature of having the quasi-isometry with the combinatorics of the group. So it's very interesting, I think, from many points of view. It seems very basic.
Okay, so I guess I probably not have time to do the full construction, but probably a lot of us have seen the rank 1 construction. You have like rank 1, say H2, and if you have two loxodromic elements, say G1 and G2, and if their attracting fixed point and repelling fixed point are sufficiently transverse, then this group, you can take the group generated by these two elements, and then this becomes a free group of two element, and then you can play this ping pong dynamics also in the flat variety. This is due to and then
so what you're claiming is any Schottky group that, say we have a thin group or some arithmetic group, and then we pass to a subgroup which by TITS, which is free on two generators. If we can always choose those to be Schottky and hence Anosov. In other words, this theory will apply to these groups that we often construct by passing to the Zariski dense free subgroup.
Yeah.
That's very nice. Okay.
So okay, you ask like whether this can be checked, and then for Schottky you have the limit map. It's just.
It's very useful in some problems, I'd imagine, where you start off with a group, you're trying to do some counting, you're only using Zariski density, so you pass to this subgroup, still Zariski dense. And for the subgroup, you can start doing this ergodic there. Yeah.
Yes.
While the original group, you might not be able to, well, we don't know how to do it. Okay.
Yeah, so the limit map is like the boundary of Schottky is can be identified by like infinite words, like with the generator. Then say G1, G2, like G1, it may be like.
Okay, that's an example. We understand it, I think.
Yeah, so this is just infinite words.
And that's very
nice. Respect to the generator. Okay, and Hitchin representation.
Sorry, these Schottky groups are inside PSL2C, right? So you are playing the ping pong where, like on which space?
But you can do it more generally. You can do for arbitrary semisimple group.
Okay, so could you do this? Like, could you play for PSL2R cross PSL2R?
Yeah, you can do this. You can do this for any semisimple big group.
But are there conditions on the eigenvalues of the semisimple elements in an Anosov group? At least that's the case for Hitchin representations.
Could you repeat that again? Sorry, I didn't get it.
So are there conditions on the eigenvalues of, say, the semisimple elements that you would use to generate this Schottky group? I mean, at least for Anosov representations that are Hitchin, there are conditions on the eigenvalues.
This is like in Tit's theorem, you know, you can, if you have how you call it, a dominant eigenvalue which pushes direction, then you can play the ping pong. Like
right, there is also equivalent definition in terms of eigenvalues, but he used the Cartan projection, but if you use the definition using Jordan projections, so that would give a condition on eigenvalues, yeah. But they're all equivalent to each other.
So true, okay. So true or false. So every group constructed by ping pong is an Anosov with respect to something. Is that what you're saying?
Yeah. But the sincerity is that the definition of Schottky group is usually given by construction rather than like a property of group.
But I'm not sure it extends to these things that, like for the hypergeometric, some people have, Brad and Thomas showed that plays generalized ping pong. I'd be very
exactly, yeah. Mm-hmm.
That's also satisfied, yeah. I don't know.
That's my problem. Like I'm not understanding if suppose I have something Zariski dense subgroup inside SL2R cross SL2R. If I play the ping pong, then whether if by ping pong I know free immediately, then I don't have any support to say immediately that it is a thin.
Yeah.
Because because property T will not help me.
I think there's ping pong now is, and especially him, he's got these generalized ping pongs which show the group's infinite index, and the generalized ping pong is on the projective space, but relative to a much more complicated set. I think it's, anyway, it's a good question, and my feeling is that this should be sorted out, be very nice.
Yeah, just one small thing. So suppose we prove these group Anosov, like something which is inside Zariski dense subgroup inside SL2R cross SL2R, whether I geometrically finite and Anosov, whether I would be able to say something about thinness.
Something about
thinness. Maybe this is more for Peter can comment.
So the point here is that you assumed you're Zariski dense, and sometimes you'll be in a position where I give you the generators of the group.
Yes.
And you have no idea whether you are finite index or not. That's an undecidable problem. So if I give you the generators, you might be sitting on a group and you actually don't know anything. But what you're saying is if it's well, if it's Schottky, okay, I think it's a separate topic. But maybe let him explain the Hitchin thing. I want to see the Hitchin thing.
Yeah. Can I just ask a very stupid question? What does it mean what is this playing the ping pong? It's like, does that mean, is that a method to deduce that you have a certain free group or a free subgroup? Or?
Yeah. It's like,
yes.
So playing ping pong is where you choose the players. Usually you have a group.
Right.
This is Titz's big insight. And if you have a group which is a Zariski dense in a linear group, and it's semi-simple, then you always have a free subgroup which is still Zariski dense. But he chooses those two elements to play this, to be far apart and to be proximal and to play ping pong. But in many problems that we're interested in, the group's given to you by monodromy. Here's our generator, and you can't choose the players. Then it's very hard to decide. But this whole discussion was, suppose we know a little bit and we know the infinite index. I think this for later. I think Minju, you must continue with your lecture, otherwise you will really run out of time.
Do you want to hear this or?
Yeah, I think so.
Okay.
No, the Hitchin.
Okay, so
very
you have the case set R. Now you have inclusion to PSA, say DR. That this is like irreducible inclusion given by the irreducible representation. Then you have subgroup gamma, then you put it over here, and then connect the component of, okay, so like the composition, let's say call this rho, and then connect the component of, so gamma, yes, and the R, rho now is this here, and then think, was it Hitchin? I think it was Labrie. Labrie showed that
gamma should be a surface group.
Yeah. So this is a surface group. And then Labrie showed that the component which contains this composed representation is Anosov, and I think the proof is quite involved, and I don't know about the proof, but for example, one property of Anosov subgroup is that this is stable under perturbation. So for this one, this representation rho, you can see that this is not Zariski dense, but although it is not Zariski dense, you can take the limit map which goes from the Gromov boundary to the flag variety of PSLDR, which is complete flags. And then I think, okay, so if you do, so this is, okay, boundary gamma, you can think of this as flag variety with respect to PSL to R. And then say if you have like KE1, where K is in SO2, then you look at the flag KE1 contained in the KE1, KE2, and so on, then this is a boundary map. Then if you believe that this is stable under perturbation, at least you know that this is also not through the full component. I think the proof is more involved for that one, but at least you know that this is true. And the finally 3 is I was originally planning to do, so G is the product of PSL to R. Now you take, say, 2 representation, rho 1, rho 2, which goes from the fundamental group of closed surface of genus G to PSL to R. Say that they're not conjugate, so they are in a different hyperbolic structure, and you define gamma, the pair of rho 1 gamma, rho 2 gamma, where gamma belongs to then if you take my definition too, then well, if you don't have this vector, then the limit map zeta is just comes from the Miller-Sparks lemma, the boundary gamma going to that one. So there is an identification going from rho gamma to boundary gamma to rho 1, a boundary of H2 coming from rho 1 and rho 2, and using this you can cook up the this boundary embedding.
That's Anosov.
Yes, that's Anosov.
Okay. That's very interesting.
Okay, yeah, I think I did not explain Harrison-Sullivan measure. So it's going to be okay. I will not explain Harrison-Sullivan measure, but let me just write. I'm going to define rho and Margulis-Sullivan measure. So to define this, I want to give a coordinate. Give a coordinate for G using maybe P plus P minus E is the the algebra of A. I should divide by, I should put G mod M, but let me just, allow me to just put G here. The coordinate is given by G maps to G plus, which is an abbreviation for maybe G minus, G minus, G plus, and some, okay, something which we did not explain. So this is called Iwasawa cycle. I did not explain this, but you can completely ignore this. Just this is some co-cycle which takes value in A, and it's coming from Iwasawa decomposition. So, but you will not you will not lose anything if you just ignore this red colored ones. Okay, so like when we select a measure, it's defined using this parameterization with the coordinate. You have some measure nu one. Okay, okay, so given Patterson-Sullivan measure, say nu1 and nu2. Now you are given some Patterson-Sullivan measures. I did not explain this, but let me just let me not enter that. But suppose you have some measure there, then you can define measure on G using this coordinate. There's some density function you can totally ignore, which is psi 1 sigma G.
Patterson-Sullivan measures live on the flag graph on G mod P.
Oh yes, yes.
Plus, but you're doing a plus and a minus.
Yeah, because it's minimum parabolic, you can identify this. So you have some density function. Okay, so associated to this, associated to each pair, you get a measure that is first left gamma invariant measure on G. And then secondly, this is not a product measure, but this is locally equivalent to the product measure 1 to 2 times Lebesgue measure on A. Okay, so for us, what's going to matter, for us, what will matter is the following 4 pairs of Patterson-Sullivan densities. So in the 1 to 2, we only consider what's going to be important for us is the following cases. U sub U, U sub IU. Okay, so I did not explain Patterson-Sullivan measure, but let me just mention for if gamma is Anosov with respect to the minimal parabolic subgroup, then you have a one-to-one correspondence for every unit vector inside the interior of the limit cone. You can associate a Patterson-Sullivan measure, which I'm going to write nu sub U. So for every unit vector inside the limit cone, you can associate, there's a one-to-one correspondence between unit vector and some kind of Patterson-Sullivan measure. So this U stands for that notation. And what is M0? M sub naught, M naught is K invariant measure. So M naught is a K invariant measure. So it's the unique invariant measure of the proportionality on the flat variety, because G1P you can identify as a K homogeneous space. Okay, so if I put this M0 in the definition, then this Bowen-Margulis-Sullivan measure is what we used to call the Haar measure. So this the Bowen-Margulis-Sullivan measure, for this one corresponds to Haar measure. And this one, we write this BMS measure for direction U. And this is called Burger-Roblin measure. U, and here it's a Burger-Roblin measure. So you put star for some technical reason, and then so this it gives an answer. Answer for 2. Okay. Maybe I just state the main theorem and finish. Sorry, I didn't get to explain the.
It's okay. There's a lot of stuff. Okay. Always invite you.
These measures are all explicit. These measures are all explicit, right? These measures.
Explicit in the sense that you can write down, or like.
Is it possible?
Yeah. So this is so this is an expression, and or maybe you meant something different. We can talk later about that. Yeah, so the decay of matrix coefficients. Say you have gamma is Anosov with respect to P, minimal parabolic subgroup, and if you have two local functions, then let me assume that M is connected. So M is the subgroup contained in the maximum complex subgroup that commutes with A. And you have a version that this is not for the case when M is not connected, but it gets more involved to write down. But let me just write the easier version. If you have this, then you have e to the 2 rho minus psi gamma TU times matrix coefficient for this measure. This converges to some constant depending on U and the measure that I described. And U so this is the main result, and I originally intended to explain, like, once you have a mixing, then there are related notions as expanding equidistribution of expanding Hall spheres. We have that, and also there was.
Okay, my suggestion is, since this is good past, let's formally end the lecture. So let's thank the speaker.